Hello, friends, schoolmates, classmates, batchmates, and to my neighborhood. Okay, thank you so much for this YT channel sharing of information so that you can receive also information, particularly regarding to science. Now, again, I will be able to continue my problem solving in chemical reaction kinetics. Okay, problem number 5. Hydrogen gas plus bromine gas will react to produce 2 moles of bromine. Okay, and here is a table for the reaction, and then you're asked for the rate constant to compute for the rate equation constant. Okay, something like that. I'll show you the problem. Okay, so I'll just be able to get the answer, but so that we will learn and will practice. So we should not solve it. Okay, and then if we get the correct answer, that means our solution is really correct. Okay, or our analysis is really correct. Okay, so H2 B Br2 is equals to 2Br to HBr. So hydrogen gas plus bromine gas is equals to, okay, hydrobromic acid. Okay, just like hydrochloric acid, right? So we have a table. Looks like this. Okay. There's my pencil case for pens and pencil pens. Okay. So we have trials 1, 2, 3, or experiment 1, 2, 3 experiments. 1, 2, 3. Okay, like this. Trials 1, 2, 3. And the second column will be the concentration of H2, which is 0.002 initially, 0.02, 0.06, and then initial concentration for bromine, 0.01, 0.02, and 0.01. Okay. Initial rate, or R, the unit here is, okay, moles per liter second. Okay, so this is 2 times 10 to the negative 3, 4 times 10 to the negative 3, 1.8 times 10 to the negative 2. So the rate is expressed in moles per liter second, and then first trial 2 times 10 to the negative 3, second trial 4 times 10 to the negative 3, and third trial is 1.8 times 10 to the negative 2. Now I will convert it to exponential because I don't want to deal with exponentials. Okay. This one. convert with figure, it will become a point something. Okay, 0.002, 0.004, and 0.018. Okay, now we are asked for the K. So this one, so take the equation and get the rate law first. It's K. R is equals to rate constant. Okay, concentration of H2 raised to the power M, and BR raised to the power N. M and N are reaction order. Okay, these are formula to be used. K rate law or rate of chemical reactions was to rate equation constant or the rate constant times H2 raised to the power M and Br raised to the power N. Okay, so we need to get one by one for H. Okay, H2 concentration first. Oh my god. Raised to the power, and what will be our rate? This one. H2 raised to the power and it's equals to what our rate. So what will be multiply a factor of this fish initial to obtain this one. But since this is the same, no change at all, so you will go directly to first trial initial concentration to the third trial because there's no changes. It's not your concern because your chemical reaction is not showing how fast or slow your chemical reaction, so there's no movement or changing or changes like that. So consider this 1 and 2. So by visualization only, 0.02 times 3 is equals to 0.06. So you can go it directly. So H2 multiplied by the factor of 3, 0.02 times 3. Okay? So this is H2 times 3. Okay, so the concentration H2 times 3. Okay, and then our rate law, rate here is rate here is 0.002. And then if you consider this first initial concentration 0.002, okay, and then you should also consider number 3, which is 1.8 times 10 negative 2. So what you considered here, your initial concentration, it should also be your rate to be considered. Okay, so like this. So 0.002 multiplied to something to get 0.018. So how can we do that? So we let R is equal to the factor, then equal to 0.018. Okay, so 0.02. Okay, R is equal to 0.018. Okay, so R is equals to 0.018, sorry, 0.018 divided by 0.002. This is 9. R is equals to 9. So your R is equals to 9. So initial concentration of hydrogen times a factor of 3 is equals to our rate law, which is 9. Okay, like that. So use this equation now, H2 raised to the power M, and substitute this 3, your factor. So 3, naubos na yung mga pen ko. Wait for a while, I will get up and do it back. Wait for a while. Okay. So this is 3 raised to the power m is equals to r, which is equals to 9. Okay, like that. So 3 exponential to m, or raised to the power m, is equals to 9. So what you will be able to multiply by itself, because this is exponent that will be equal to 9. So that is 3 times 3 is equals to 9. So, okay, 3 raised to the power 2, because you multiplied 3 by itself 2 times. So that is 3 times 3 is equals to 9. So your m will be 2. Okay. So 3 times 3 is equals to 9. 9 is equals to 9. M is equals to 2. So our M is equals to 2. Okay. Because this is 3 raised to the power 2 will be equal to 9. So our M reaction order of initial concentration of H2 is equals to 2. Okay. So second order initial concentration of H2, 2. Okay. Now for Br here, so Br raised to the power n is equals to R. This one. Br raised to the power n is equals to R. We'll just get this second part here. We'll just get the second part here. Now again, the same principle. So what factor you will multiply, and we are now in the second column. What factor you will multiply to 1 from the second experiment, first experiment, to get this second experiment. Okay. And then if you use this first initial, use this initial concentration, use this also the rate for this first experiment. Okay, and if you use this 0.02, use also the rate for the second trial. Okay, like that. Okay, so you multiply 0.01 times 2. Okay, so that you can obtain 0.02. Okay, that is, you are using trial 1, trial 2. So that is initial concentration of bromine times the factor of 2. So our rate here, our rate, okay, so you should multiply by a factor of 2 also. See, 0.02 times 2 is equals to 0.004. Okay, same as here, 0.02 times 2, like that. Okay, sorry, 0.01 times 2 equals to 0.02 initial concentration of bromine. So the same thing here with the rate, with the 2 you choose. Okay, so times 2 shot. So R is equals to 2 directly, and then 2 raised to the power n is equals to R. Substitute the factor you use, which is 2 raised to the power n is equals to 2, which is the R. Okay, like that. So solving this equation, 2 raised to the power n is equals to 2. So simply R is equals to 1. Okay, oh no, n not R, n is equals to 1. Okay, 2 raised to the power n is equals to 2. Since the same base, it should be cancelled, both cancelled, and n is equals to 1. So this is first order. So first order reaction of bromine, first order with respect to bromine initial concentration, so n is equals to 1. Okay, so our overall reaction order is n total is equals to 3. So we have a third overall reaction order for this, okay, sample problem. And now we solve for the value of K here. In solving the value of rate constant K, you need to plug this initial all, this first experiment, not the second, not the third, because that's initial. We mean here the initial. Okay, so H2, okay, R over H2 raised to the power 2 Br raised to the power 1. Substitute this values from here to here and solve for the value of K, okay? Like that. So R is 0.02, that is uh, molarity second negative over 0.0002, sorry, so power 2, that is molarity squared, and then 0.001 molarity. Okay, so we need to cancel this one. Okay, cancel like that. So 0.02 times 0.02 is equals to times 0.01 1 2 3 4 5 6. Okay, then 0.02 times 0.02 divided by 0.02 times 0.02 is equals to times 0.01 1 2 3 4 5 6. Okay, and then this one 0.002 times 0.002 divided by 0.012344. K is equals to 500. Okay, K is equals to 500. Ang unit niya kay cancel. So, and then cancel by 1. So m squared second, like this. So this is the value of K, 500 1 over m squared second. 500 over, the unit will be 1 over m squared second as a unit for our rate constant in this chemical reaction. Okay, this one, given this data. Okay, it's very easy, right? Okay, if you know really the concept, then you can understand. The value of our rate constant is 500 1 over molarity raised to the power 2 times the second. If you want the m, capital M and small letter s to be on the numerator, then it's gonna be negative, or 500 m to the negative 2 and s negative 2, something like that. Okay, don't be confused. Okay, like that. So now we need to prove if this is a third overall reaction unit of K, right? So we have the formula of K. K is equals to n, 1 minus n is equals to times like this. Okay, you will substitute that here and you will obtain also the same unit, 1 over m squared times s. Okay, like that. So you can substitute that here, so that you can obtain a unit of 1 over square meter second. That is our answer, but it is the unit of the third order reaction. Okay, and overall reaction order 3. Okay, because that is from here. Okay, 2 plus 1 is equals to 3. So meaning to say, this is the unit of the third overall reaction order, 1 over m squared seconds. Okay, by following this rule, R is equals to K times H2 raised to the power n and B raised to the power n. Always let the reaction order M and N, but also it depends on you. It could either be X and Y, like that. But this exponent's reaction order has nothing to do with the number of moles beside H2 and Br2, because this is not a stoichiometric relationship. This is only that through experiments. The exponential reaction orders you will be able to get that one through the experiments 1, 2, 3. It cannot be computed through the stoichiometric relationship of the number of atoms, the number of moles. That's only the difference in the chemical calculation. Okay, so that's the difference. Okay, like that. So if we have now this answer, then we can also try to, you know, estimate that to the relationship like that. For example, if you increase the K, your rate of chemical reaction also increasing. Okay, if you increase the K to, let's say, 500, and then your rate also will increase. Okay, because K is the rate equation constant, or the rate constant is directly proportional to your rate law chemical reaction. Okay, like that. You understand? So if you have a small value of K, your initial concentrations are expected to be lower. And then if you keep on increasing the initial concentration, okay, the number of your rate constant will go high, because that is inversely proportional with each other, because the initial concentrations H2 and Br2 are in the denominator. So inversely proportional with the rate constant. As you increase the rate constant, okay, the initial concentrations will decrease, and vice versa. If you increase the initial concentrations of H2 and Br, your rate constant will be increasing the same as the R, because R and K are directly proportional with each other. Okay? Then as you keep on increasing the overall reaction order also, okay, the rate of chemical reaction also goes fast. Okay, or increases also. Okay, like that. As the number of order increases, the rate of the chemical reaction also increases. Okay, that's very clear, huh? Okay, this one, like this 3. If this overall reaction order will become 4, 5, 6, 7, 8, 9, 10, your R, rate of chemical reaction, will also increase as you keep on increasing the reaction order. Okay, as you keep on multiplying a factor increasing number from your initial concentration, your rate law also will be increasing, something like, okay. Okay, it's very clear. Okay, thank you so much for watching this little video of mine live streaming. I hope you like it, and then please subscribe my YT channel if you haven't subscribed yet, and then click the notification bell from some newest updates of I am seeing my channel. Thank you so much for listening for this chemical reaction kinetics problem number 4. Bye bye. God bless everybody.